everyone, this is a video to go over lesson 2.7 part 2 where we're looking at derivatives for the first time. So last day we talked about the slope of a tangent line at a specific point x equals a. Today we're actually just going to give that a name, and so the derivative of a function is actually the slope of the tangent line at x equals a. Okay, so we're just giving it a new name today and doing a few more examples. So we have the same formula here as we did before, and I'm just going to say here it's the instantaneous rate of change at x equals a, but it's also the slope of the tangent line. And we have some new symbols to learn. So when I talk about the derivative at x equals a, I use a little prime here, a little dash here at the top. So f prime of a is actually saying the derivative at x equals a. There's other notations for derivatives as well. That's because two different mathematicians discovered calculus at the same time, and they each had their own notation. And so there's more than one way to write the derivative. So if you're talking about y instead of f of x, then you would say y prime would be the derivative. You can also say dy by dx, or d of f of x over dx. Those all mean the derivative. So you'll see those pop up, and I'll remind you as we go through some examples. Okay. Let's look at example 1. It says, given this function, x squared minus 8x plus 9, find f prime of a. So that means find the derivative at a general point x equals a. So I'm not looking at a specific numerical value this time. I just want to find the general formula for the derivative. Okay, so I'm just going to use my formula that I know for derivatives. F prime of a equals limit as h goes to 0 of f of a plus h minus f of a all over h. And again, we can't just plug in h equals 0 because you'd be dividing by 0. So we have to use some derivative tricks, or some limit tricks. Okay, so I'm going to plug a plus h into the equation and a into the equation. So I'd get a plus h squared minus 8 times a plus h plus 9. That's f of a plus h. Minus, put this in brackets, a squared minus 8a plus 9 all over h. So notice I put the f of a in brackets so that I'm subtracting that entire function. Okay, and I'm just going to simplify this a bit. So I'm going to expand out the brackets. Actually, I'm going to start on a new line because I don't think I'm going to have enough room. It's important to write your work out neatly here because there's lots of terms to think about. Okay, so a plus h squared, that would be a squared plus 2ah plus h squared. I'm going to expand that bracket so I have negative 8a minus 8h plus 9. And the only thing I have to do for the second part is just put a negative on each term. So negative a squared plus 8a minus 9. And that's all over h. So that's a lot of terms. Okay, and there's lots of cancellations that happen. So let's just go and look at like terms first. There's an a squared and a negative a squared. Those cancel out. There is a negative 8a and a positive 8a. Those cancel out. There's a 9 and a negative 9. Those cancel out as well. So once we've made all those cancellations, we can see that every term that's left has an h in it. And we use a different color to cancel the h's. So we're free to cancel one h from every term. So there's not much that's left. Limit as h goes to 0 of 2a plus h all over 1. So now I can use the direct substitution property and just plug in 0. Oh, I think I forgot something. Yep, I did. I forgot one term. I forgot the 8h. forgot to cancel one of those h's. There we go. Okay. There, that's better. So there was an h canceled from 3 terms on the top and 1 term on the bottom. That's better. So now I can plug in h equals 0, and I get 2a minus 8. So I'm just going to write the answer here. A equals 2a minus 8. So that's the slope of the tangent line at any point. So the advantage of finding a little formula like this is that now, let's say I want to know the tangent line at x equals 1. I could plug 1 into the formula and get the slope of the tangent line. So this is a nice way to find if you're interested in many different slopes. So I could find note, this gives a formula for the tangent line slope at any point x equals a. For example, let's say I was interested in the slope at x equals 1. Then I would just plug 1 into the formula, and I would find out that the slope is negative 6. Okay, so you can do that for any point. All right. So let's do an application. So a manufacturer produces bolts of fabric of a fixed size, and the cost of producing X yards of fabric is 40 root X, where C is the cost in dollars. Okay, so what is the meaning of C prime of 100? Okay, let's just look at the units. The units is going to help. So remember, slope here equals change in y over change in x. So y, in this case, is C, or cost. It's measured in dollars. And x is yards of fabric. So C prime of 100 would be the instantaneous rate of change in the cost per yard of fabric when x equals 100. Okay, so I'm going to write that out. C prime of 100 would be the instantaneous rate of change in cost per yard fabric when 100 yards are being produced, or I'll write are currently being produced. So writing out the units for me, anyways, is helpful when I'm trying to interpret what a slope means. So they're asking us now to find the rate of the instantaneous rate of change at 100. So I'm just going to write my formula down for slope, and this time I'm given a value of a. So I'm going to get an actual numerical value out as my answer. C prime of 100 is limit as h goes to 0 of C of 100, oops, wrote 2 C's down, C of 100 plus h minus C of 100 all over h, and I'm going to plug both of those into the equation, so I get 40 times 100 plus h minus C of 100 is 40 times root 100 all over h. Oops, I forgot to write the limit. Limit is h goes to 0. And simplifying that a little bit more would be h goes to 0, 40 square root 100 plus h. 40 times root 100 is 400. h. And in this case, I would use our multiply by the conjugate strategy. So, because I have got a square root. So I'm going to multiply the top by root 100 plus h plus 400, and the bottom by the same. So remember, if you see a square root and you're trying to calculate the limit, you want to try multiplying by the conjugate. So it's just taking the square root and then the same exact terms except using the opposite sign between them, and then expanding. So we're just going to expand the top. So 40 times 40 is 1600. Square root 100 plus h times square root 100 plus h is just 100 plus h. You can save some time here because the middle two terms, when you expand, they're going to cancel out because they're opposite signs. And so I'm just going to write the last two terms. 400 times, or the last term, 400 times 400 is 16 with 4 zeros. 1, 2, 3, 4. Yeah. And on the bottom, I'm not going to expand it. Because there's no cancellations when you expand it anyways, so it's a little bit of a time waster to do so. Okay, and in the numerator, I can expand that a little bit further by multiplying in that bracket. So I'll have 160,000 plus 1600h minus 160,000. All over that mess on the bottom. 40, 100 plus h plus 400. Now, in the numerator, you can see these constant terms completely cancel out. And also, the numerator and the denominator both have an h. So we can cancel those out. So now I can write my limit. Limit h goes to 0. On the top I have 1600, and on the bottom I have 40 root 100 plus h plus 400. And so I can plug in h equals 0 now because it is defined at that point. It writes values for some reason. So we get 1600 over 40 times 100 plus 0 plus 400. And that gives you 1600 over 800, which is 2. And we need some units. So remember, our units, if we look back above, are dollars per yard. $2 per yard. So let's interpret that for a second, because that was a lot of math there. So we used our formula for the slope of the tangent line at 100. We plugged that in. We noticed there were square roots, and so we used the multiply by the conjugate strategy. We simplified. We canceled out some h terms, and we got down to the answer, which was 2. So what that answer actually means is when this company is producing 100 yards of fabric, and let's say they want to start increasing production, if they increase production by 1 yard, it's going to cost $2 extra. So that's what that means. The rate of change in cost per yard is $2 at this point for the company. So they can use that when they're deciding whether or not to increase their production. Okay, one final example is for another velocity example. So last day we saw an example where we dropped a ball off the CN Tower, and this one is talking about a car. So it's giving us this position function here. And so we want to know what the instantaneous velocity of the car at time t is. So we're going to use our formula for rate of change, for the instantaneous rate of change, or the derivative. So we want to know v of t. That's just limit h goes to 0. And our function's not labeled f here, so I'll use s. S of t plus h minus S of t all over h. So in this case, I replaced the a's with t's, since this question specifically asks us to look at time t, not a. Okay, and I'm just going to plug those into the formula. So I get t plus h squared minus 10, and S of t would just be t squared minus 10 all over h. And I'm going to expand it, and hopefully there'll be some cancellations. So this is limit h goes to 0. So the t plus h squared expands to t squared plus 2th plus h squared. And the negative can be expanded into the bracket, give negative t squared plus 10 all over h. And some like terms cancel out. The t squareds cancel. Negative 10 and positive 10 cancel. And now after I've canceled those, I notice there's an h in every single term. So I can cancel those out. So I get limit as h goes to 0 of 2t plus h all over 1. And now is when I can plug in h equals 0. So the velocity at time t is 2t. So now I'm going to use this formula in part B. So it says find the instantaneous velocity after 10 seconds. I don't have to redo that whole limit this time. I can just use my formula I calculated in part A. If I didn't do part A, then I would have to use the whole formula for t equals 10 seconds. But for part A, I found the velocity at any time t is 2t. So my velocity at 10 seconds is 2 times 10, which is 20. And let's just look at the units that I'm measuring in here in meters. It doesn't say, oh, it says 10 seconds, right? So I know it's meters per second. I'm just going to write here. We can use this formula. Good. And find the average velocity of the car over the first 10 seconds. Question C here. So remember, the average velocity is the slope of secant line between t equals 0 and t equals 10. So we can use the slope formula, rise over run, or change in y over change in x. So it would be s of 10 minus s of 0, because I'm going between 0 and 10 seconds, divided by 10. So s of 10, if you plug it into the formula, is 90. S of 0 is negative 10. So I get 100 over 10. So that's 10 meters per second. So the average velocity between 0 and 10 seconds is 10 meters per second. So notice that's different from the instantaneous velocity at 10 seconds, which is 20. Okay, and here are your required questions. And that is all for the second half of 2.7.